almost the end of the session. Again, if you have questions how to run contests, test cases, yeah, like anything.
Yes.
Okay. Yeah.
And
Yes,
I'd
Jan.
like to know where we can access the past videos, because you just said that this meeting is being recorded. So how are we going to access it?
Yes, there is a YouTube channel, Women Coding Community on YouTube, and you can find their playlist that's created for this summer bootcamp. Oh, we can see it on the screen now. Perfect. Totally. Yeah, you see?
Yes, thank you so much.
Perfect. Okay, now I feel like we are good. Now we can start with next topics. And Lily, please unmute yourself.
Yeah, let's start recording. I'm starting recording because
Yeah, perfect.
So, okay, recording started. Today we are going to discuss hash map, hash set, and prefix. So these two separate LeetCode patterns. And the topic is quite easy compared to binary search, which we discussed last week. Basically, there is not that much theoretical material, but in context, so basic, what is the agenda for today? I will explain hash map and hash set. I'm pretty sure that you all know it, so it will be a theoretical material, very short one. Before I head, then I will show how to solve one of the tasks, which is we will discuss during the class for the class. And another one I will just cover quickly for homework. They are also pretty straightforward and easy one. Then we will move to another topic, which is prefix sum. And there we also will solve one task in class, and one I will just cover slightly. This one will go for homework. So yeah, let's get started. Hash map. So mainly hash map and hash set. It is used for, it's not like a two-pointer where we discuss different patterns and templates. It's mainly for optimization to reduce time complexity for n quadratic to n, but it always will consume the space complexity. So let's get started. A hash map, also known as a hash table or dictionary, depending on the language, it's data structure that pair a case with value. So this one, the illustration, how it looks like. So for example, we have key Apple and we have value, which is associated with this key. Hash map is incredibly efficient because all the operation like lookup, insertion, deletion are typically performed in constant time. Yes, moving forward, properties of hash map. Data store in form of key value, as I mentioned already. Hash map don't store duplicates. There is no duplicates. Every key in hash map is unique. Value could be duplicated, but key should be unique. Hash map unordered data structure. So what does it mean? When we're speaking about array, it is preserve order, but it is not about sorted order. It's about preserving order, how you're inserting your elements. So for example, you insert apple, then you insert banana, then you insert ananas, for example, or something, and it will preserve the order how you're inserting it into data structure. When we're speaking about hash map, it doesn't preserve order. So this is the main things which is you should remember. There is time complexity. Okay. Moving next. Do you have any questions about the hash map? Because I'm moving to hash set now. Okay. Oh, moving on. Hash set. Hash set, simple underneath it is hash map. What is the difference? It is a simple form of hash map, and instead of storing key value pairs, it's just store unique keys. When to use hash map or set? So common use case of hash map, including implementing dictionary, counting frequency, storing key value pairs, and halting scenarios requiring quick lookups. Common use case of hash set include storing unique elements, marking elements as visited. In trees, there will be always a hash set like seen or not seen. These notes we will cover it during the trees and graphs topic. Checking for duplicates. Okay, what is spotting keywords where you should think whether this data structure during the solving LeetCode task or solving interview task? So it should be like unique, duplicate, frequency, count, anagrams, exist, lookups, pair, sum, groups, buckets, map, track. So let's take a look. 1 second. This is okay. So yeah, I covered theoretical material around the hash set and hash map. Do you have any questions before I will move to the solving task in class?
Lydia, can you just explain what is the main difference between hash set and hash map if both are storing unique keys?
Yes. So what is the difference between hash set and hash map, right? You're asking?
Yeah.
So hash map, as I explained, it's usually contain key and value. So if in task you need key and value, then you will use hash map. Regarding the hash set, it's just a simple form of the hash map. Let's say this will be on this side, this apple, banana, and carrot, there will be a hash set. So usually, for example, your traverse array, where you have three, for example, here we have like, let's see, let's go 2, 2, and 2. You traverse as an input like something like this. And during the interview, you can solve like you ask to just found unique values, and that's it. You can, in this case, you should use hash set because you just care about uniqueness. So, for example, this on the right side, this will be hash set, which will preserve just unique because it doesn't allow you to insert non-unique elements. You can't insert twice time 2. It will be collapsed. It will be collapsed, and in the hash set, you will see only unique. But if during the interview, you will ask to have frequency of these elements, like you receive input array, and you need to count the frequency of the all elements in the hash map in the array. Then you will use a hash map here and count frequency. So 2, it will be unique elements from your data store, and your count it's there is 3 times you meet 3. Then you will use a hash map here. So it will be looks like this. Does it make sense?
Yeah, it makes sense. So if the question is return only the duplicates, even in that case, we should use hash map, isn't it? Because we won't know which are the duplicates until we count the frequency.
No, you don't need because hash set is data structure which doesn't allow you to save duplicates. So you can, if you need to find only unique elements, just go straight forward to hash set.
No,
if you
the unique elements. What I mean is, if in that array sequence 2, 2, 2, 3, 3, 1, right? If the question is return the list of elements which are duplicate. 1 is not a duplicate, so my list should only have 2 and 3. So in this case, I do need to count.
No, you can use still hash set because when you're inserting, so for example, I want to insert, it will return you false or true. false, I believe it means that there is already duplicate. And true, it means that you actually successfully insert. There is no elements. So you can use hash set in this case. How it will work? You will build hash set, and you will trying to put two or another operation which is contains also will return you true or false in case if this element is already in hash set. And so, for example, in this case, what you can do, it is maybe not an optimal solution. Here we just in context of hash set, you will create another array, which is your output here. And you will do this code. So for example, you're doing for a loop where in your nums initial one, which is this one, you will go and here you have your hash set. And you will try to put, you will put 2 and you will ask contains 2. First won't be contain. Second will be contain, and then you will fill up your array with what with the duplicate number. Does it make sense?
Yeah, okay.
Yeah. Moving. Okay. So first one, it's quite. I heard it from my friends. I don't remember whether I was asked during my interviews somewhere to solve valid Sudoku, but it's quite frequently asked task during the interview. So description will look like this. You will given a Sudoku board. Does someone know what is this Sudoku board, or I can cover like spend 1 minute just to explain what is this Sudoku board?
Can you explain, please?
Yeah, sure. So Sudoku board, it is I'm not sure if so. You're given board which is 9 on 9 size, 9 elements in the row and 9 elements in the column. You need to solve this to be solvable. I believe it should not contain any duplicates elements in the row or any duplicates elements in the column. And also there is it will be splitted on the small grids boxes, which is 3 on 3, and in every these boxes there should also not be duplicates. So you should fill it with only unique elements. This is Sudoku board. So yeah, as we already know, there should be uniqueness. Then we are saying that this valid this Sudoku board is actually valid or not. So you start thinking, okay, maybe I can use a hash set here or hash map. In particular task, which is very important, note you ask to determine whether the current state of the board means the input, the initial original input is actually valid. It's not like solvable. You just need to verify that the current state of the board is valid, not solvable. This is the main notes from this task. So means if it's solvable, given this is the description. Determine if the current state of the board adhere to the rules of the game. Each row and column must contain unique numbers between 1 and 9, or be empty. Represent a 0. I'm not sure what is that. In my case, there is dots, not zeros. It is dots. So dots, it's fine. Each of 9 free on free subgrids that compose the grid must contain unique numbers between or empty. Note that you are asked to determine whether the current state of the board is valid, given these rules above, not whether the board is solvable. The description is clear now. Okay, cool. Here, you're given board, which is in this column contain 2, 8. That's why we are returning it's false. And there is another one board, which is true. It is valid one. There is no duplicates. There is one row contain 8, this one, but none of them in column or on grid. Okay, moving. Intuition. A simple way to check for duplicates in a row is compare each numbers with every other number in the row. This takes a lot of time because you have to search the whole row for every number. I mean, you can like take every row and just to compare if it's contain duplicates or not. Instead, we can use how we can optimize here. Instead of ending up with n quadratic, I think it's even n in cube should be. Instead, we can use a hash set to make this faster. As we go through the row, we add each numbers to the set. If we find the number that's already in the set, we know it's duplicate. And check is constant time. So now we could keep track duplicates in. We can do this. Column, identify row, and column is straightforward. Okay. The idea is understandable here, that how we can check whether in the row or in column we have duplicates number. So for each row and for each column, we will keep a hash set. And we will adding the numbers in this set, and that's how we will validate if our Sudoku board is valid or not. This is half of the task. Is it clear now?
I didn't quite understand the approach you're taking. Can you explain that again?
Yes. So see, we have this board. We have input, which is 9 on 9. In order to check every row, whether it is duplicate, you can go with linear time, just to with not linear, with quadratic time, where you for each numbers will go through the row and validate if the element is present or not. But instead of doing it in quadratic time, you can introduce hash set. Hash set per each row. Per each row means you will have 9 hash set for each row. And also you will have a hash set for each column. And on the way, while you're traversing, you will adding each element. Here I have examples. So for example, you have this one row. Initially, your hash set will be looks like empty. Then you will adding one element. Then you will adding a second element, because you will emit. You don't care about dots. Once you meet dots, you will just emit. But if there is number, you will add to your hash set. Then you will adding 5, 3, and on the last, you will find duplicates. So 2 is already in the hash set, and you will return false. So you can return false right away because your dashboard, your Sudoku board is not valid. This is straightforward with row and call. But also, we need to cover this scenario. Regarding now, it's more makes sense for you about the row and call.
Yeah, but you're saying that we're going to go through each number in the row and add it to hash set, right? So
yes.
And we'll do the same for column. So isn't it still O of n square?
No, it will be n, because when you're doing for a loop for row, for example, you're taking e in array, and then you need to introduce another one for which will be e plus 1 in array. This will be O quadratic, because you're taking one, for example, element, and you try and compare this element with all these numbers here. Then you're taking 3, and you go along all the array again. But when you're using hash set, you just once going with your with iteration over the row, and you're adding them in hash set. That's it.
So are you saying that the moment we come across a duplicate, it is just easy to return false and end the thing there, isn't it?
Yes.
But I have one more question. You said that we will need to take the sum of the elements. Will the sum be always same for 1 to 9 if there are duplicate elements, right? I mean, I didn't understand the point of taking the sum. Why do we need to take the sum?
No, why you need to take sum?
I thought you said we should take the sum.
No, we don't need to take sum. You're just using hash set. You have this introducing hash set. You are putting while you're iterating over each row.
Yeah.
You're adding into hash set elements, and once you will ending up with duplicate one, you will figure it out because hash set will return you that 2 is already present in my hash set, and that's it.
And how does it ensure that we don't? How does it ensure the columns? This is the row-wise hash set, isn't it? But how does it ensure there is no duplicate in the column?
For per each column, you will introduce another hash set.
Oh, okay.
So yeah,
Thank you.
it will looks like this. See, we have sets per row and we have sets per column here.
Makes sense. Okay.
9 of them. Okay. The tricky part of this task is really only this subgrid. How we are going to figure it out if in this subgrid is duplicate one. So we can figure it out one formula here. There is indexes on the top and on the left. You have indexes 0, 1, 2. You have indexes 3, 4, 5. You have indexes 6, 7, 8. This is the size of our board. If you will divide it on the 3, all of them will be equal to 0. Another set of these indexes, if divided on 3, will return you 1. And this set of indexes will return 2. So based on this formula, we will reduce our indexes to 0, 2, and that's how we can identify. So for example, this subgrid will be our subgrid, which is 0, 2, 0. This subgrid will be again 0, and this one will be 1. So that's how we're going to figure it out, whether these subgrids, and per each subgrid, we also will have a hash set in order to check if these hash sets are contain any duplicates. And code will look like this. So at the beginning, we will initialize empty one row sets per each row. We will initialize column sets per each column. It will be 9, and we introduce our subgrids, which will contain 0 to 3 not inclusive index, and 9 also not inclusive here. So we start traverse over the our board, where R is row, column is column, C is stand for column. We will find if we will take num. If num 0, or in our case it will be chart, it will be like dots, then we will continue because we don't need to check them. Otherwise, we will check if num contains is in row set, or in column set, or in subgrids. And then if either is contained, these duplicates will right away return false. Otherwise, we will add these nums and we'll traverse and we'll move to the next num in our valid grid. Does it make sense?
Lilia, could you just quickly show me the grid again? I just want to snap of it with your index. Thank you. That's it. Thanks.
Yeah. This is the most trickiest part of this task. So you just need to remember how to find this formula, how to divide this subscript, and that's it. And it will be associated with hash set every subgrid, and that's how you can check whether it's contain duplicates or not.
Lily, I've got a quick question for you, if you don't mind. Is this a common approach, or is this common in interviews where you've got to split a grid up into subgrids? Because I would never have thought of doing it this way. So does it come up a lot in these problems?
This the tricky part of when it comes to this task, you're asking me if it's common approach or not, right?
Yes, and if a lot of these problems that were asked at interview have this sort of scenario where you've got to split a grid into subgrids.
Common approach of it's common approach for this particular task. I mean, valid Sudoku, because it's what is the common here, that you're using hash set to identify whether it's duplicates or not duplicates. This common approach for task when you're asking to identify whether in your initial data structure there is something duplicates or not, and you can figure it out that you need hash set. But particular about this task, common approach is to divide to find it's not like common approach. The tricky part of this task, particular to valid Sudoku, there is another valid Sudoku task, which is a hard one. I believe it's also including dividing and find subgrids. But just one thing which is you should know about this task, that you should use a hash set. It's very straightforward to understand how to use hash set with row and column, but it is a little bit tricky to figure it out how to use hash set with subgrids. So particular to figure it out about this formula.
Thank you. I just love the subgrid approach. You just remember it. Thank you.
Yeah, this is kind of probably you should remember, but it's nice if you understand how we come up with this formula now. So that's it about the valid Sudoku, how we're using hash set. If there is no other questions, I will move to homework task. We'll just slightly explain how we are going to use, I believe it will be hash map or hash set in the next one. If we're okay, I'm moving. Okay, cool. Homework will be group anagrams. You are given an array of string. Group the anagrams together. You can return the answer in any order. Folks, do I need to explain what is the anagrams means?
Yes, please.
Yeah, sure. So basically, anagram it is word. So for example, if you look at this, net and tan, they contain the same syllabus, I believe, letters, the same letters. They contain the same letters, just in different order. So we call them anagrams. And here, see, we have 8, it, and t. They contain the same letters, but in different order. So this group of anagrams, this group of anagrams, and this one just, but he doesn't have any anagrams in our input. So the task is just to find anagrams and return a list of them. So that's it.
Will they have duplicate letters like EAT, but you can use it, some letter duplicated?
Ask again.
I understood like equal amount, all letters should be same in 2 words, but and order is indifferent. But can letter amount like 3 in it, can it be 4 or 5 if we'll duplicate some letter in it?
I will just move here 1 second. So you're asking if, for example, this word will be still anagram in this group?
Yeah.
No, it won't. Yeah, it should be strictly all the letters, just different orders.
Okay, thank you.
So no, in this case, what we are going to do, we are going to use hash map here. Why hash map? In these things, we are going to have a unique key here. I'll just briefly explain it. This is homework. Key will be, so for example, we're taking any string which just comes with our input. So for example, this word is come first. We make some modification here. We assorted it. It will be this one. We sorted. Why we sorted it? Because if we will sort all of them, 3 words, they will they will have the same unique key. So we just need to find something which is common between them, and it will be our unique key, which is we will identify if this group of words is actually having the same. So we sorted them, and we introduce here our hash map, which is have this key. And when we traverse string, the array of string, when we're modifying just one, we will modify it. We will ask if it's contained, but we will put here original one. See, I have C, which is my key here. Let me maybe make it this one. E. As string is immutable, means whatever I put here, I make a char of key, then I sorted it. It's not impacting my original one. This one original. So basically, once I identify the key, I'm putting here original one, because I created map, which is taking string and list as the value. And here my key. So that's it. And at the end, once I will traverse all the input, I will return my output, my solution. It will look like this. That makes sense. How we use in this case hash map. Okay, I told it's very easy this week.
I just have one more question. So if the word is, for example, mood with double O, and the anagram is doom with double O again, DOOM. So the double O's, will it also consider as two separate characters?
Double O, if you have like this word.
MOOD or something like that, yeah.
Like this.
Mm-hmm.
And you need to find the anagram. I mean, this is one, we'll go the separate one.
Okay. Mm-hmm.
We are not reducing anything. We're not removing duplicates, anything.
Okay. So it will consider as one character.
Yes.
Okay,
Yes.
got it. Thank you.
Okay, prefix sum. So prefix sum. What is prefix sum? Prefix sum is a powerful technique used to compute sum of elements in subarray efficiently. Instead of calculating the sum from scratch for every query, we pre-compute an array where each element at index I represents the sum of elements from the beginning up to I. So this is the basic idea here. We have our original array, and we pre-compute prefix sum. First it's 10, then we 10 plus 15 will be 25. 25 plus 20, it will be 45. Here will be 55 and 60. So this is how we are calculating our prefix sum. And this is the idea of prefix sum, to make a pre-computable data structure. Is it clear? what we can do now, after we pre-compute our prefix sum, we can answer different queries. So given array of size n, create a new array prefix such. So we created here, we can answer different questions here. So for example, if we need to find prefix I, we can quickly find them prefix I minus. So for example, if we need to find this query, we will figure it out. It's 55. We will just take, we will sum up with 5, and we will answer what is our prefix I. Other queries, this is a simple one. So for example, but usually it's used for this kind of queries. When you need to find, for example, answer for this subarray, what will be here the sum for this element, for this subarray. For this subarray, we need to take prefix j and minus everything. What so for example, for this, let me draw this one. So this one will be our, what is the, so for example, we want to answer what is the sum in this subarray, what is it's equal. For these things we need, we know, we have knowledge what is our prefix j here. We know this prefix g is equal 55. We know that this part is equal 25. In order to give answer what is this equal for, we are taking 55 minus 25, and we will have answer like 30 here. This kind of queries, which is we can answer in constant time because we have already prefix sums pre-computed initially. This is the idea of having prefix sum. Instead of doing otherwise, if, for example, you will be asked and you don't have this prefix sum, you should need this computation to make this computation during answering your query. So it means you need to find the whole sum, or you're just traveling to the I and J and then pre-compute it. So it's take more time. It will take time because you need to traverse to make this computation. But otherwise, if you have this prefix sum, you can in constant time answer the question on this query. This is the idea of having a prefix sum. And yeah, is it clear?
Not quite. Sorry. What is sum of I and j? Is it the sum of both arrays?
It is sum between indexes I and j. I could be here. So for example, I could be here, and you need to find then some for indexes. You will be asked to find, for example, sum of the subarray between I and j.
Subarray of both the original array and the prefix sum array. Is that what we want?
No. So for example, let's close this one. You don't have prefix sum, and now you're asked to find sum between I and j here.
Right.
So we can use we can do this pre-compute in real time when the queries just come. So for example, you're doing some calculation on your initial array, but instead of doing a calculation on your array, so for example, your application is just answering the queries of different, you need between the different intervals to find sum. In this case, we're doing what? We are having a pre-compute prefix sum, and we can easily find answer, because to find answer, we know sum of this one prefix sum, right?
Yeah.
Of this array. And in order to find answer for this one, we just need to extract this part from this part, and that's it. And it will give a constant time of answering.
So if, for example, like you showed that I and j, Yours is 55 minus 10. So it should just result in 15 plus 20 plus 10, the sum we were going to get. Okay.
You need out of 55, just extract 10. This is the formula.
Makes sense. Yeah. Thank you.
And yeah, no. And if will be question and I it's 0, so it's basically prefix sum if j. This is something also keep in mind. We will when we will solving task. This one also understandable, right? Why we return just prefix j here. Okay. So to build prefix, it will take O10 and space complexity, and answering it will be constant time. Probably let me explain homework because it's very straightforward task, and then we will move to the in class, because the one which is we're going to cover in class, it's a bit tricky one. So this one, one of the also like not popular, but sometimes you can be asked during the interview. So the idea of this task, it's homework. Given integer array nums, handle multiple query of the following type. Calculate the sum of the element of nums between indexes left and right, inclusive, where left less or equals right. Implement num array class. Initialize the object and implement the function, which is will answering our queries. Is it clear description? Okay. Return the sum of the element of nums. So it's everything what we need to do while we initialize our class num array. We make pre-compute prefix sum here, which is int nums, and then we will just answering our queries as I explained it before. So using these formulas and returning result instantly. So this is the idea. First pre-compute array and then answering ranges. I'm moving to another task at it, if everything is clear. Okay. Here's some subarray. This is 100% very popular task during the interview. Very tricky one, in my opinion. It has different forms. We will cover in classroom the most popular. Then on Slack, I will share slightly different forms, but idea will be the same, almost the same. But yeah. Okay, moving to the description. Given an array of integer nums and integer k, return the total number of subarray whose sum equal to k. A subarray is continuous, non-empty sequence of elements within an array. We have examples. So this is our original input, and we need to find subarrays which is equal to which is sum equal is 2. And our output we have seen 2 subarrays here. This one, then this one. Its description is clear.
Can it not be 0 element as well as the second element? So could it be 3 subarrays? If what I mean is you took 0, 1, 1, 2. Can we also take 0, 2 indices?
0, 2, no, because non-empty sequence of element within an array. You need to find subarray. They should follow each other.
Okay.
Yes. Okay. The brute force solution will be looks like this. So we need to iterate through every possible subarray, checking if the sum equal k. So it takes O10 quadratic to iterate over all subarrays and finding them of each subarray takes O10 time, resulting in n triple, I think, complexity. Where so this is the solution of the brute force. So we have count. We will start from start. We will take this first element. We will start to traverse the rest of array, and we will try to find sum which is equals to k. And if we will find, then we are having then we will increase our count. This is not optimal at all. This is a brutal force solution. Moving. Since we're working with subarray sums, it's worth consider how prefix sums can be used to solve this problem. The sum of subarray between two indexes I and j can be calculated with this formula, as we discussed before. So this is again the examples, which is we discussed before. I hope it's clear on this moment. Okay. So yes, if we're using prefix sum, so all pairs, we need just to find, we are looking for k here. We know this formula. It will looks like this, all values of, so yeah. Now, we're trying to unify those two formulas. I will explain why, in order to use in our solution. So, because, yeah, just 1 second, I will think how to better to explain this one. Prefix sum, prefix sum. I will skip for now unifying this formula. This is not very important, but we will cover. I will explain why we need to unify, but there is two approaches where we can unify, where we can actually having different tricks. So let's just now what we need to understand. So we have input of array. We need to find all subarrays which is equal to sum. We figured out our brutal force solution, which is take n triple, which is absolutely non-optimal. And now our thinking is, can we use here prefix sum to find the answer? We're trying to fit, we know that our prefix sum can answer this formula, which is will suit us because we're looking for subarrays, subarrays in particular sum. So we can try to fit this technique to this task. Okay, but there is one thing which is we need. This is the tricky part of one of the tricky part of this task. 1 second, I'm trying to figure it out how to explain it better. So we have this prefix sum, and here to prefix I. One issue with this is when it's valid. To make this unification possible while avoiding the output, we can pretend to prefix sum array, making it possible for prefix to equal 0. So we count prefix sum, build prefix sum. This is file to subarray sum to k. Okay, we can solve this. One of the approach, we're moving to the second option, how we're going to solve it. So as we know these two formulas, where we need, where our subarray actually started from 0, and another prefix when we have I, which is more than 0. There is tricky part to how to solve it. If we're going to unify our solution, it means that we are not going to check every time whether I is more than 0. Then we should unify the solution. But there is bottleneck. So, for example, if I will be 0, 0 minus 1, we will end it up with out of bound exception. We can handle it with different approach. Other one approach I discuss here, and it's very common one, and we will use it in the optimal solution as well. I will come back to this because we need to understand why we need to pretend 0 here. Otherwise, this case could be handled by adding just of this condition. We will check if I is 0, then we just return prefix sum j here, or we're going with this formula. Does it make sense what I'm currently speaking about?
Not exactly. Why you so here where you said that line which says sum is equal to I equal to 0, you're just saying that that's the condition. I didn't understand.
Yes. See, you will have different subarrays. So, for example, in this example, we will look for k, which is equals 3. You will have right away this subarray, which is 1, 2, and which is started from which is will satisfy our condition. This is prefix sum, which is started from 0 elements, and it will equals 3. How we're if we will take a look at this example, so our prefix sum here, which is j, it will equals 3. Assume that our j is pointed to 2 here. But our prefix sum, so for example, if this one prefix, which is starting, so basically you are looking for this array, right? 1 second. So here will be, it will be I, and here will be j. This subarray, which is starting from I and j, you need to find the prefix sum here. If we will use this formula without handling this edge case, which as I mentioned, I will be our 0, means your prefix sum here will be minus 1, because your I is pointing to 0, right here. And here you're pointing to 1. And you will ending up with, if you're not going to handle this, you will ending up with an error out of bound solution, out of bound index. Does it make sense? So means you can't right away use this formula. You should handle this use case, because ideally this use case is this one, covered this formula. When someone asking you to find prefix where I is 0, it should looks like this.
Yeah, that I understood, like why we have to handle I equal to 0. I understood that. But if you like just scroll down to the code, what I'm where we were looking, not here.
Oh, this is optimized one. Yeah, 1 second.
So here when I equal to 0, for example, in this case, we will for I equal to 0, I less than j, I plus plus. Is it this one? I thought we were looking at another different.
No, it's this one. See, what we are trying to solve here, we're trying to find subarray, which is equal to k. In order to find this subarray, what we're taking prefix sums, which is j. It's usually the one which is starting from 0 and finishing the j. So it's the longest one. You're trying to extract any prefixes from 0 to up to j not inclusive, and to find if on this way you have this subarray. So for example, 3, 4, like -4, 6, and 7. and this continues another array. So here you try, you have your j here, which is pointed to, this will be your j, which is 7, and this is the whole prefix. And in order to find here all the subarrays, which will be equals to k, what you're doing here, you're just trying to extract all the prefixes before 7. You first extract 1 from 7, then you are checking if it's equal k. Then you extract 1 and 3, and you're trying to figure it out if there is a subarray which is equal k. So,
Okay.
but there is some edge case where e is equal 0, and we can't right away use this. We need to handle it, this test case, this edge case. There is two options how to handle it. One is to explicitly check whether e is 0, and then you choose what you are using, prefix sum or this formula. Otherwise, more common solution is to build a prefix sum. Instead of building this way, pretend 0 as 0, then it will work. And there is
in this, if you just scroll down a little bit where you were checking, no, not this one, the previous code. So here we won't have out of bounds exception, because you're always, I mean, I is anyway starting from 0, isn't it? So why would this result in an out of bounds exception?
there is won't, but you will lose this case, use case, you will lose one array in the, I believe it won't, but here you will lose case. So for example, this one, you won't count one subarray here. This one, 1 and 2, because you will start from 1 and 2, and 2 minus 1, because 1 is 0. And you will never cover the use case where actually it's starting from 0. It could potentially lead that you won't count subarrays, or it could potentially lead to out of bound indexes.
Okay.
Is it clear, folks? So yeah, in how to handle this case, we will pretend I 0, and when we are building our prefix sum, as I explained it, so basically you can use this this condition, or you can build your prefix sum starting from 0. So it will just be moved the rest, shift the rest to the right. This is how code will looks like in this case. So we will build our prefix sum. This is the how I'm going to pretend it. And it will build this subarray. And once we will build the subarray, so we can run this formula in order to find out if the k, if we have subarrays, which is equal k, and increment our count. So this is, we reduce time complexity to n quadratic. Next, I will show the option where we can use actually what it will be. It will be our hash map in this case, because we need to track frequency. Okay, is it clear here about the second solution? Okay.
Lilia,
Yeah.
is it possible to share your slides? Is it Excalibur? Can you share them before the session or during the session so we can follow? I think it maybe be easier to follow when there's a lot of movement on the screen.
Yes. Yeah.
Is that possible? Thank you.
Yeah. Yeah. So yeah, this this is I put a dry run for a few iterations. So basically, if you not pretend prefix sums to 0, where we have this 0, so you won't cover this one, and you will ending up just to count this one. So basically, you will lose one subarray from your answer. Okay. Yeah, this is the explained part, why it's important to handle this case. Now going to optimization. Now going to optimize solution with hash map. So basically, we can figure it out that we basically don't need to use exactly this formula here, which is we use here this one. We don't really need to use this one, but we can use another one, which is this one. Because we know prefix sum, we can calculate it in real time, and we know k, and everything what we need to know if we ever met this one prefix before. If we met, then we can be with 100% sure that there is subarray which satisfy our requirements. Does it make sense how we're ending up with this formula? So in this case, we can use hash map to preserve all the prefix sums, which is we have seen. But here is another things which is also very important. We need to track frequency. Why we need to track frequency? Because could be prefix sum, and hash map, as we discussed, has a key which is unique one, and could be before different subarrays at the beginning, which is returning the same value. So that's why in this case we need to have hash map and track frequency of the prefixes before. I'm explaining here in depth because for me it wasn't clear before how the frequency can help here. So yeah, so we're taking as an example this one nums. There is each steps which is equals which is for different variables, which is different starting from the first iteration, where current prefix sum is 0, what is prefix map looks like. Then we're moving the second iteration, which is taking first our num1. Prefix sum at this point will be 1. Our sum still will be the same. And we are trying to calculate this. If current prefix sum minus k ever see prefix this one before, it doesn't. We don't have anything which is -2 at the beginning, so no. Then we're moving forward. We're taking index 1, which is equals to 2. We are calculating the prefix sum, which is 1 plus 2 will be 3 here. So our prefix sum at this point will be it is actually after we calculated. We calculated if 3 minus what is this 3 minus 3 will be if we see before because we have pretended. Yes, this is optimized solution is also required to have an initial pretended zero value, which is also doesn't make sense what I'm saying. That we have before we will go, we will initialize our hash map with pretended sum, prefix sum, which is equal 0. And we say that, yes, there is one frequency of this element. In order to cover these cases, when we have current prefix sum 3 minus 3, we already have it because we know this. We're speaking about this subarray, which is started from the index 0. If we won't have it, So we will lose this subarray, but it should count towards our output. So this is the pretended one, edge case. Another one, frequency. Once we will, it is this one. Once we will reach index 5, it will be this subarray. We will count prefix sum, which will be equals 6. 6 minus 3 will give us 3 prefixes. And we know that we already met a few subarrays which has these prefixes, because we are tracking our prefix sum map. And we count towards our solution 2 here, because we can actually have 2 subarrays with which on this line up until to this index 5. We know that there is 2 subarrays which is equals to our condition, and we're counting towards +2. What I mean here explicitly, so this is our original array, and here we are looking into this subarray. And we have different subarrays. Once we've calculated, one is this one, 1 and 2, and another one, this one. And we can actually build the different subarrays with this. Yeah. So does it make sense now or not? Means we have different subarrays which are starting from different indexes here, different type, which is can actually have sum which will be equals to 3. So this is two things which we need to handle as a part of our optimal solution for some subarray. One of pretended sum, which is 0, and another one we need to track frequency of the prefixes, which is we've seen so far, because these all prefixes are valid answer and will contribute towards the answer. So maybe it's not the best explanation. Let's walk through the code, and maybe it will become even more clear here. So we initialize our prefix sum with initial value, which is cover our start of subarray. Current prefix sum at this moment will be 0. We are iterating through the all arrays in nums. We're calculating our prefix sum. Here we have condition prefix sum minus k if we ever before met any prefix which is satisfied this condition. If yes, then we count our output. Then we increment our output. If it's not, and if it's not, then we just not increment our count. But after each iteration, we are preserving this current prefix sum in our prefix sum with frequency. If there is 0 frequency, it will be remains the 0. If there is needs to increment the frequency, then it will be incremented by 1. So basically, that's it. That's how we are using prefix sums in this task.
Sorry, Lilia, this was a bit confusing, but I have a question. You know, prefix sum array is a cumulative sum array, right? Like, because you are adding the elements as you go from 0 to n. Now, if you just scroll up, for example, and show me any initial array. Okay, let's see that 1 to any. My question is, so nums equal to 1 to 1 minus 1 to. Okay, yeah, if you can stop here, please. So
Yeah.
here we have 7 elements in the initial array. Let's say the k value that I want is 0, where the sum is 0. So that is satisfied with 2 elements in the middle, isn't it? 1 comma minus 1.
1 second. Yeah, I will answer. Can you repeat your question? So k will be 0 in this case.
yeah, let's say the use case we want to look for is where k equal to 0. And
Okay.
the question is, if the prefix sum array is a cumulative sum array of the initial array, then how do we get answer for questions where k value is coming from a subarray that is in the middle of the array and not from the start? Does that make sense?
Why? How you say again?
For example, like take this one, k equal to 0. How would you get the, how would you do this? I mean, how does that solution work where k equal to 0?
Yeah. So basically, in optimal solution, I will dry run optimal solution in this case to explain. So basically, first will be your prefix sum here will be equals 1, right? First, it will be started. So initially, we initialize it as 0. Once we will come to here, it will be 1. So we will, so our prefix sum will be like this, plus 1. It will be 1. Then we will go and check. We also initialize our, then we're trying to figure it out, this formula. Just will copy it. So why this formula currently? We figured out that this one, prefix j, minus prefix 1. So basically what we are looking in this task, we're looking to answer, to find any subarray between j and I, which is equal to k, right? In this task. That's everything what is asked. Now we can slightly modify this formula and look if we ever met before this prefix sum by this formula. If we met, then okay, we know that there is subarray which is equal, because this is formulas are the same. We just come up with this solution. And this one we can preserve in hash map and check if, so while we were iterating, there is no pre-compute at the beginning, as we discussed before, for another task or for the solution where it is quadratic time. In the quadratic time, we did this prefix sum, and we have array, which is help us to answer questions. Here we're doing some different tweak with prefix sum technique. Instead of doing pre-compute, what we are doing, we are using hash map here, and we're storing prefixes. It's similar to what we're were doing with to some unsorted array. We also was saving some answers before in order to answer them. So basically, we are not doing pre-compute array. This is the difference here, but we're still using prefix sum technique here to find the solution. Okay, now this one initially, our prefix prefix sum j in this example will be 1, right? Now we are trying to answer this prefix j. It's understandable why it's a 1, because I'm currently working on first elements here. Next, I'm trying to find to answer condition. If to answer this formula, this one, prefix sum j minus k. So here we are checking 1 minus 2. If it contains prefix,
K is 0, isn't it? Why is it minus 2?
k is 0, sorry, because I took it, yeah. So here we are answering contains 1, right? Not minus 1, it's just 1.
Okay.
We are checking our hash map initially contains only, will be our hash map which is contains only 0. 0 it's prefix here, and 1 is just frequency. So we're checking if we ever seen 1 before. No, we don't. We are not increment count in this case. Our count will remain 0. But we want to preserve this prefix j, this one, in our hash map. In our hash map, which will be 1 at this point, right? Because we are preserving not this one value, not this one. We're preserving what we have, prefix sum. This is the prefix. So we're preserving it here. It will be 1. Oops. Which is, we saw once. And this one is our prefix, which is currently equals I minus j, I minus 1, right? Or it will be just I, prefix sum, which is I become. Does it make sense?
So,
yeah.
So you know where you computed prefix sum of j equal to 1, you said we are not pre-computing the prefix sum array, but how did you end up getting prefix sum of j equal to 1 if we did not pre-compute that array?
We are doing it in real time. We're doing it here. See, this one, current prefix sum. What we're doing, we're taking this current prefix sum, and during the iteration, we are summing up with num here.
Right.
This is our prefix j. All the time, we are just summing up. We are not coming back from the start of our array. We just all the time counting new prefix sum. Next, instead of now, we need, so for example, we have this one array. It's our prefix j here now. We're trying to find out if there is we ever met any subarray which is equal to k. And in order to find if it was equal to k, we will use this formula. We will take from prefix sum j minus k, and we have hash map which is storing all the prefixes which is we've seen so far and the frequency of these prefixes.
Right.
I will explain why we.
Here is where I have a question. We are storing all the prefixes we saw so far, isn't it?
Yes.
Those prefixes are cumulative sums. That is, you are going to keep adding each element to all the other elements before, and then keep adding that as the key, and your value is how many times you saw that, correct?
Yes.
Now, how will you then end up with a result where our k value is 0, because 1 comma minus 1 is in the middle of array, but that prefix sum will never be will never satisfy that because it's a cumulative sum. Like as you go on, move forward in the array, it's the sum of all the elements, previous elements in the array.
Yeah, let's do dry run until. So this is subarray, which is will actually satisfy our condition, right? Here.
Yeah.
So let's do dry run. Here we have our prefix 1. We say if it's 1. Then we are doing next. Our prefix j at this point will be free, right? We will check free minus 0. We will check if it contains. It doesn't. Then we put here our hash map will be now 1 and 1, and then here will be 3, and here will be 1. We are saving all the prefixes. Next, there will be 4, right?
Yeah.
Next, we are checking 4 minus 0. We will end up with 4. Then we will extend our hash map here. It will be 4 and 1. Next, we will have free here, right? Because -1 is come.
Right.
So here will be 3 minus 0. You will figure it out that in hash map, you saw already these prefixes, which
Okay.
is equal to 3. So
Yeah.
basically, you know that there is one prefix, means if we will take this one, 1, 2, 1, 1, minus 1, we will extract this subarray prefix, which is we saw so far. We will we will find out subarray which is actually equal to 0.
So can you just keep going? So now can we increment 3 key value 3 to 2, and then it becomes, no, as in the hash map, you have to now increment that value to 2, isn't it? Where for the second.
Yes.
So, okay, now you go to the next element, which is 2.
2, yes. It will be 5 here.
Yeah.
Now 5 minus 0, we haven't seen, so we will put this one. Next, it will be 6, right? Right, it will be 6 here. Again, 6 minus 0, we will put 6, 1. And next, here will be 6 minus 2, will be 4. Right? Again, we will find solution. So it will be 4 here. We know that we made this prefix.
Yeah.
So basically, found another one. This is subarray. Which one? 1 second. Should be, I believe, it will be this one, subarray. This one. -1, 2, 1, and -2, which is will equal to 0 as well. So, and we know there is prefix. This is the prefix. This is the prefix.
What I'm not understanding is,
which is 4.
sorry, what I'm not understanding is how as you're populating the hash map with the prefix sum and the frequency of that sum, right? How do you know which particular key value pair is satisfying your condition over there? I didn't get that. Are you getting my question?
No.
So, we went on populating this hash map, right?
Yes.
1, 1, 3, 2, 4, 2, 5, 1, 6, 1. So this is, by the time we finish this array, this is the final hash map we have. Now, how are you able to say that I have 2 arrays in this, because 2 arrays that satisfy my condition k equal to 0, just by looking at that hash map, which is just a key value pair of prefix sums and frequencies.
So we have this formula, right, against which we're checking our condition. So it is the same. We figured the prefix technique is answering on the queries, right? To answer the queries, we're taking prefix, which is the longest one. We extract what we don't need, and we know if this, that's how we are looking for the sum of a subarray between J and I. This makes sense, right, for you? How we usually, what is the prefix technique at all? So prefix sum, it can answer if the sum between I and J is actually equal to K. This is the idea of prefix sum. How it's answered? Because we usually have a pre-computed prefix array, right? Where you have from A to G, for example, you know the sum, and how to answer if the sum between I and J is actually equal to K. So you need to extract I part from J part. And this will be equal to a subarray prefix. Does it make sense?
Yeah, I think what you're saying is every time we
And this, yeah, in this solution, it could be confusing you. What we are doing here, we are just tweaking this formula because we know that how we can answer to this question. And instead of tracking k, for example, we are tracking all previous prefix sums, which is we met so far, in order to find if there is subarray is equal, because this one and this one is from the input we know already. This is known variables, so we can use them in order to find prefix sum, which is we saw so far, and in order to answer if we are just storing all the prefix sums as before. Yeah, go ahead, ask questions now.
No, I mean, I think I understood now. So what we're saying is every time we see the same prefix sum, it means that there was an array that satisfied our condition where k equal to 0, because you, instead of just finding where k equal to 0, you actually found the element where the sum was already seen. So that's where you incremented the count, and what we are getting is that count. And so, okay.
Yes.
That makes sense. Thank you. So we don't increment the count until we see the same prefix sum again, isn't it?
Yes. Yes. Yes.
Yeah.
So yeah, first we're checking. This is also ordering is very important here. I will cover, folks, regarding the frequency as well. Now just we'll cover this part and frequency also. So the order is very important here. First, you calculate prefix sum, which is j. Current prefix j is the longest one. Then you trying to answer the condition if we saw prefix I, which is the shortest one before, how we can answer if we have it in hash map. If it's not, then we don't do anything. We not increment count. We increment count only if we saw it. Then only after this, we are putting this one, current prefix sum, j, which is the longer one, in our hash map. We are not putting this one condition. We're putting this one. This order is very important. This is clear, right? Ordering. Feel free to ask questions, folks. Okay. Now regarding frequency, why tracking frequency in this case is important. Let's take this example. You can also, after I will share this board, there is all the steps is, for this one. Example is covered. So I'm thinking how to explain better, starting from this one. Visualization when frequency 2, previous prefix sum 3 was at I and 3. For the subarray 2 and 2 for I. Both sum 2 are unique. Okay. 1 second, I'm checking my notes. Okay. So this is quite, if I will start from example, for example, I think let's start it from the beginning to make the same dry run rather than starting from the middle. So prefix j in this case will be 1. Our hash map in this case will be 0, 1. Then it will be 1 and 1. Also correct me, folks, if I will make some mistakes in my dry run. So next we will cover this one. It will be 3. We will try 3 minus 3. It will be 0. We will find one count. Count will be incremented here because we will satisfy our if. Also, it will be go 3 here. It will be our first time when we see this prefix. Next, we will go it will be 4. It's again will be first time when we see this prefix. Next, it will be oops, control them. It will be our free here. I think I need also to figure it out how to increment. So first 1 minus 3, it will be minus 2. We are not incrementing. Here next will be 3. It will be 3 ones we met, then 4 ones we meet. There will be 3. So we will increment here by 2. You following me, right, folks? I'm on this index now. Next will be our 5. Here, 5 we never see before. 5 will be our 1. And next we will have 6. 6 we never saw before, but it will satisfy minus 3. It will give us 3, and we will ending up here. So let's look at this. Why it's important? Oh, so we will be here. We're looking at this array, and we know that there is 2 subarrays, which is will meet our condition. In this case, it will be this one, 1, 2. It's it will be this one subarray. And in this case, it will be this one subarray, which is equal to will satisfy our condition. So on this prefix j, we will find 2, which is also saying the same for us too. There is different prefixes, which is this is one prefix, which is we saw before. It's 1, 2, and this is one another prefixes, which is 1 and 1. All these prefixes start at a different I. And it's starting from this I. That's why we are count all this frequency, because we have the same prefixes I with the same value, but starting at different I's. And all of these prefixes contribute into subarray, which is we're actually looking for. And it's building different subarrays. That's why it's important to track frequency of the prefixes I, which is we saw so far. Otherwise, if we won't track it and we will use just hash set, we will say, okay, yes, we saw it, but how many we don't know. Prefixes, and we will say that yes, there is one prefix which we saw, and there is one just subarray. Does it make sense? Okay. Any other questions? We have 20 minutes left. Probably the same. We can, Moina, if you have some questions, don't hesitate to ask.
No, it's good. I'm good. Thank you.
Okay. So yeah, it's tricky one. It's a tricky one even for me. That's why probably it's not was not very clear how I explained it. So this is the homework and contest. Valid Sudoku we cover, subarray sum equals key we cover, group anagram I explain it, and range sum I explain it. Thank you, folks.
Yeah, hello.
Hello.
Yeah, hi. It would be helpful if you could share the whiteboard for